Hello, my name is Andres Mejia, and this is a small area estimation at two levels in the Colombian Saber exam. The Saber exam is a compulsory exam for a highly skilled to be graduates for all the last year's students, and it's basically a census of the population of the students graduating in that period. In addition to the tests that are shown on the screen, it recompiles socioeconomic information in a socioeconomic survey of the students. Our main data that we'll be interested in is the global score, so to keep that in mind. The data we are using is of the second call of the exam in 2021. The data was anonymized, and we have more than 330,000 students available. The socioeconomic survey includes variables like those shown on the screen. All of these variables are categorical except the last one. For example, the number of rooms in the households has some ranges, 2 to 3, 3 to 4, 4 to 6, something like that. Another thing that we'll be talking about today is something to do with the political division of Colombia. Colombia is divided into 32 departments, and each department is divided into municipalities. There are 1,118 total. Those municipalities will be our small area. Okay, how is a typical survey designed? First, a population statistic is chosen, in our case the mean global score of the whole country. Then a probabilistic sample is built. In our case we built an stratified sample using the municipalities and strata with at least 5 students for each municipality, and considering the variances of the last year test, and we finally got our sample of 38,000, about 38,000 students, and we use an estimator, the Horvitz-Thompson estimator, and we report the error and the result. As our sample was big, the error is then small. But what happens next? This same data is used to estimate the same statistic in other small areas. So we have 1,118 small areas to calculate the mean score in each municipality. The thing is that the standard error from the municipality depends directly on the sample size, and we have very small sample sizes for some municipalities. Most of them are 5, and others are even lower than that, because that's the whole population of the area. We can see that the error tends to be higher when the area is smaller, and also keep in mind that this scale goes up to 40. When we calculate this, we see something like this, that these are our global scores, and this is the area information. But we also have all this information, socioeconomic information, that we are not yet using. And here we have to make a distinction. The socioeconomic information is part of the sample frame. That means that we have that information for individuals in the sample and individuals that are not in the sample. But the global score only will be known for individuals in the sample. So what happens when we try to integrate this socioeconomic data to our process of estimation? We have to include a model to link them. So we move from a design-based framework to a model-based framework. And the model we are proposing is this, that is a two-level hierarchical model, in which the score of a student depends on the matrix X. The matrix X is the matrix of socioeconomic data with the data I've shown before, and two effects. One effect U sub 1 for the department, and one effect U sub 2 for the municipality inside the department, and finally an error for each individual. Each one of these variables, U1, U2, and the error are distributed as a normals with mean 0 and certain variances. Once we have estimated the parameters of the model, the beta and the sigmas, we can build an estimator for our small areas. And this is simple a mean where we use the data of that individual if it's in the sample, or the estimated data with theta is a consistent estimator of our data, the estimated score when the element is not in the sample. In order for this to have some sense, the model must fit the condition, especially the variables must be normals. Here we see that the variables have not that many problems when it refers to the normality. The residuals fits quite well. The department has some issues, especially in the left tail, and the municipality effect is a little light-tailed, but nothing to worry about. As I mentioned before, we have to report not only the value that we are estimating, but also the error, and how we can calculate the error here. What we did in this work was to use a bootstrap estimation. Basically, we took our estimation, our values, and created a new population, as if drawing new values for the U1, U2, and the error, and created another population. In this new population, we know all the values, all the scores for this new population, and with these values, we build the mean score for each area. We recover our original samples with the indices and calculate the estimators as before, and we can have an error from this bootstrap sample. We simply take the quadratic error for this bootstrap sample and average our multiple iterations of this, and this will be our bootstrap error. Our bootstrap error was done with 30,000 bootstrap samples, and the result was this. If we compare this with the standard error of the model-based estimator a couple of slides before, we see that the scale is 0 to 2 to 3, the before was to 40. They are somewhat comparable. This actually is the square of that, because that was unbiased and this is a little biased. We will see that a little later. To compare, to also see how this model behaves, not only compare with the design-based model, but we consider another two models that are basically simplifications of our two-level hierarchical model. These are simple one-level models, one with the department, one only using municipality, and the rest is the same. Each model will be estimated separately, of course. Not the betas not have to coincide. Now, how do this model compares? One of the advantages of using a known database to do this is that we know the ground truth of all municipalities. We know how the mean score in each municipality, and we can compare what we got with our estimators. And we see that in general our estimate the model-based estimator with department and municipality behave quite well. Each point here represents a municipality, and we can see that the density that most municipalities have an error quite low, and the other estimation schemes come higher. All win to the direct estimator, and ones that include municipality behave better. One thing to note is that the department one is a little misspecified, because we are calculating municipalities area but using only department data. So it has some these weird effects that we can see here. This is the same information, but for relative error, and we can see a very similar effect all around. Now, one thing we want to do is to see how this behave if we change the sample. For example, is this stable if I use another random sample? That's what we do here. We use our design-based framework to estimate the bias in MSE using different samples. I use 3,000 samples from them and calculate the bias and the MSE for our original model and for all three models that we are considering here. We can see that these models are biased, and the bias is not equal, not even in the same direction in all municipalities. The direct estimators have almost a null bias, and the others have bias not more than 5 or 10 points, but up to 25. The other thing we see is that using municipality, department and municipality gives us in average less bias than the other models. But the thing we lose in bias, we win in mean square error. We can see that all model-based strategies have at least a lesser mean square error on average than those that the direct estimator. But the thing is that even when the mean square error is smaller on average or on the most cases, there are still some municipalities that have a mean square error that is way bigger than the one with the direct estimator. Lastly, we do a model-based simulation that it's very similar than doing the bootstrap sample. The main difference is that the values used in the bootstrap samples are not necessarily coming from a sample, but are those that we can think of. And here the ground truth is not the values, the mean scores in each municipality, but the values of the parameters beta, sigma 1, sigma 2, and sigma 3. So the area scored is part of the realization of these variables, so it's again a random variable. But we can still use the same scheme to compare the results. Using this, we can see that and we have somehow flipped the papers of the bias and mean square errors with the direct and the model-based estimators. The direct estimators has a big bias, which is no surprise, and the model-based have a very small bias. We can see here these both graphs are the same, but with the direct-based removed to see the effect. We can see that both that use municipality behave quite similarly, and here is the behavior compared with sample size, that each estimator that has municipality behaves very similar. For mean square error, we can see that again that the direct estimator has some big mean square error even in this schema. But one surprising thing is that the model base that only use department that is misspecified has even a bigger, and on average a bigger mean square errors than even the direct estimator. So specification in the model is very important. But models that use municipality, this again is the same graph without this effect. It's very similar. And we can see here that all effects lower in themselves as the sample size goes up. And as conclusions, model-based approach that use municipality tend to behave better than direct estimators for most areas. However, there are some areas, particular areas, when they behave way worse than direct estimators. And the difference between a two-level nested hierarchical model and one-level model when the the model considered is the deepest one is not that much for this problem. Thank you.